this gets mapped to a solution, to the solution of W starting at phi of x. Okay? So the flow of V commutes, the flow of V and the flow of W commute with the endeavor. So this is finding the submanifold sigma and the vector field V's that are invariant for some given class of the vector fields W. It's a classical problem in the system. For example, in the case of sigma is a torus and V is the linear flow of the point. So some constant vector field of the point. So then what you will have is an invariant tori. So this is all very basic. Now, by the way, you can interrupt me at any time you want, and ask questions or clarifications if something is not clear. So now let me introduce what fluid motion means. Here we have a Riemannian manifold M with some metric G. So this is a Riemannian manifold. And here we have some fluid inside. Now we are going to suppose that it's invisible, so it has no viscosity, and it is incompressible. So it has constant density. So the way you describe this fluid is by giving its velocity field u. So the velocity of each particle of the fluid in the domain at each time t. Okay? So the fluid has a velocity field that evolves in time. Okay? So the state space of the fluid are going to be divergence-free vector fields on the manifold. Divergence-free means that there is the divergence operator, which is, you can imagine, the usual divergence operator in R3. Okay? So this will be vector fields U such that the divergence is 0. Okay? And this is because of the incompressibility. Incompressibility. The fact that the fluid is incompressible means that its state at any given instant of time is given by a divergence-free vector field. Okay. Now I will call, by the way, just to, so B free Mg, this will denote the space of divergence-free fields on the Riemannian manifold M. Okay. And the regularity, we are going to assume all through the talk that the regularity of these divergence-free fields is going to be say infinity, so infinitely smooth vector fields on the Riemann manifold. Actually, for the people studying the equations of fluid dynamics, this regularity issue is a big topic. Okay? To defining well the functional space where you are going to define your dynamical system is one of the main inputs. Okay? So we assume smooth. And now, for the moment, I have just described the state space. What is the evolution equations of the law that gives you the motion of the fluid? Well, the fluid is the Euler equation. So think that the derivative in time of the vector field u is equal, I'm going to use the same notation as there to kind of metaphorically. You have to imagine that you have an infinite dimensional vector field in your space of divergence free fields. And this infinite dimensional vector field is W with maps D free fields to D free fields. Is given by minus the covariant derivative of u in the direction of u, minus, and now this is the gradient of the Laplace inverse of the divergence of this same type. this is the Euler equation. And this term here is what is normally known as the pressure. So you might have seen the Euler equation written a lot of times this way. Derivative of the velocity field times velocity field times its gradient is equal minus gradient of the pressure. It's the same thing as there, but in a general Riemannian manifold. Right? So instead of this material derivative, as they call it in fluid mechanics, you have the covariant derivative defined by the Riemannian metric. And all that the pressure is doing is just ensuring that this map goes to divergence-free fields to divergence-free fields. Okay? You now compute the divergence of this guy, because you have divergence of this, and then divergence of this. This is the Laplacian minus 1, they cancel. That's why the pressure term is there. If you have only this term, it wouldn't be incompressible. So this is our dynamical system. And we are interested in invariant manifolds of this dynamical system. So what are those? You can imagine your infinite dimensional space, these two fields. This is the way I have to draw an infinite dimensional space. And so you imagine that you have some submanifold sigma inside. And now this is invariant if you take any initial velocity field u0 in this submanifold. So you can imagine, if you don't want to think geometrically, you can imagine that what you have is some family of divergence-free vector fields parameterized by some parameter, yeah? Some k-dimensional parameter. More abstractly, you have just a manifold parameterizing your family of vector fields. So for any vector field in here, there is a solution u of t of Euler equation for all time t, and such that, as you're going to say, such that ut still belongs to this family. Okay. So you give an initial velocity field, and the solution is a velocity field that still is in this submanifold. Okay. So
you assume the manifold has finite dimension?
Yeah, finite dimension. Yeah, I'm always assuming. Yeah, you can also define the same problem for infinite dimensional submanifolds, but we are not going to be interested in finite dimensional submanifolds. So what is interesting about these finite dimensional submanifolds is that here the Euler equation in the submanifold becomes a normal finite dimensional ODE, because this is evolving in time, so it's just the finite dimensional number of parameters that are evolving in time and giving you the solution. So now okay, maybe I'll write it here. Now the question during the rest of the talk is, what kind of finite dimensional submanifolds can you find in the Euler equation, and which dynamics can you find in these submanifolds? We define the notion of embeddability. So take sigma submanifold, finite dimensional, and this on vector field. So I say that the pair sigma with the vector field V is embeddable. Probably there are some 2Ds or 2Bs somewhere into the Euler equations on Fg. If there is an embedding, like in that case. Here you have to be careful with what you mean by an embedding into an infinite dimensional space. But for the moment we are not going to be too much concerned about this. So there is an embedding phi from the manifold sigma inside the space of divergence free fields. Okay. So that if now you take any point in sigma the vector field in N given by so ut so you take a solution of the vector field V in sigma, you follow the orbit, you map it to your space of divergent free fields, and the resulting time-dependent vector field is a solution of what? For all time. So notice that you may have heard that it is a very famous open problem to show that given a smooth velocity field, the Euler equations in dimensions 3 or higher have solutions for all time. Okay, so the fact that the Euler equation defines an actual well-defined dynamical system here is a very important open problem. Locally, it's true, but globally, we don't know. But this question, autoembeddability of a manifold and a vector field, is independent of that, really. Because even if you don't have, in general, global solutions to this PDE, you can still have finite dimensional families of solutions, of invariant solutions that exist for all time. You build, for example, a periodic orbit. Yeah, so a vector field that is periodic and solves the Euler equation, that is a solution that exists for all time. So the question is, which sigma V are embeddable? So what invariant manifolds can you build? And you are especially interested, for example, in invariant tori. Okay? That's the invariant tori for PDEs is also a very active topic. So let me give.
Excuse me, is there an issue in the definition of a manifold in this infinite dimensional space? I mean, is there an issue of the regularity of the manifold, or how do you define the...
So the manifold is going to be smooth, and now...
What does it mean to be smooth in this infinite dimension?
Sigma is smooth. Okay? So the manifold itself, sigma is smooth. And now to be an embedding, so in our case, it's actually going to be very simple. We are just going to take we are going to consider finite dimensional linear subspaces of the space of divergent free field. And then you have a basis given by k divergence free fields, and there you can define perfectly well a smooth embedding as an embedding into this dimensional subspace. And in general, you can define it by the Frechet or the Gateau differentiability of C. So there are several technical ways to do it. But if you are in the case where you embed everything inside a finite dimensional subspace, it's a regular definition. Okay, so first, there is a very beautiful result by Fao and Rousselis. So they show that if you take sigma to be an n-dimensional torus and V to be any linear flow, so constant linear flow in the torus, any n, any w, then this pair is embeddable in the Euler equations on the two torus, okay, with the flat metric. And now I will explain briefly how they perform this embedding, which is very explicit. So here, there is no Km involved, which makes it very simple and clever. Yeah? It's beautiful. So now in 2022, there is a result by Ciso, Peralta Salas, and myself. So we generalize the Faot-Crouzet's construction. So the main idea is due to them. In the case of the three-dimensional torus or any even-dimensional torus with the flat, again with the flat meter. So here, remember, n is as big as you want, so n-dimensional tori inside the space of divergence free fields in the three-dimensional or two-dimensional tori. Let me briefly explain how the construction goes.
Excuse me, what is V here? V,
V.
vector field.
V vector field.
The second result, so...
No, here the same, yeah. So same sigma, same V, but for the other equation in T3 or T2. So also invariant tori in the other equation in those dimensions.
What do you mean by no KAM?
So yeah, I was, in case some people were experts on this, sometimes when you try to find invariant tori in a PDE, what you do is apply KM techniques. So you find an almost invariant tori. For example, you have a periodic orbit, and then you perturb a little bit, and you apply an infinite dimensional version of KM to show that there are actual invariant tori solutions that belong to some invariant tori along near this periodic orbit or near this quick solution. And here, the things that they don't, the construction is explicit, they don't use any such technique.
For KM, you need the Diophantine conditions on omega in general. So.
Well, yeah, also. Quasiperiodic invariant tori. So really what we want is first the embedding. So you take your n toroidal coordinates, phi1 to phi n. You want some vector field u depending on these parameters on the two torus. Okay? So this is the two torus. So y, x. Periodic. And now you divide the two torus into n highways, in rectangles like this, and you take, so let's represent like this, B0. This is going to represent a steady solution, so time independent solution of Euler in T2, compactly supported. So they put one such solution inside each highway at a height corresponding to the θ1's θ. So for example, here you have θ1. So here you put one such compactly supported solution, θ2, you put another one, here you put another one, here you put another one. So you just translate these solutions to each of these coordinates. Okay? And now, to that, so because they are compactly supported, if you add them, this is still a compactly supported solution. But it is steady. So now what they do is they add a constant velocity field in the y direction with velocity given by each of these frequency components. Okay? So you include omega I in the y direction, and you make this compactly supported, so you take some cutoff function and you put this inside of these highways. Okay? One here, so here the one with frequency with velocity omega 1, the other one with velocity omega 2. Some of them might go in the opposite directions depending on the values. So you add these two vector fields. And you then add everything to it. And now this is still...
What's chi of x? Sorry, what's chi of x?
Chi of x is some compactly supported function, okay, that makes this constant vector field decay and become 0 before you reach the next highway. So compactly supported around the region of the variable x where each v0 has the support. Now this is still a time-independent vector field. So the fluid particles are moving, but the velocity field u, which is given by this, so this sum in each highway, this is fixed in time. And now you can check, actually it's just a calculation, that if you now begin to move these coordinates, so take phi1 plus omega 1 of t, phi2 plus omega 2 of t, etc. In other words, you take a solution to this linear ODE in top. So you are basically just moving these guys with this velocity. This time-dependent vector field, now there is a time dependence in the place where these state solutions are supported. This is a solution to the Euler equation in the two terms. So it's an invariant. So here the map is just the way to assign each coordinate to these vector fields. And now you can generalize this to dimensions 3 and 2 even dimensions by considering steady states in higher dimensions. Actually, the fact that there are steady states in 3 dimensions, for example, this is a deep recent theorem by Gabriello. So it was not evident how to generalize this construction to higher dimensions because you didn't know if you had compactly supported solution. Okay, so now a theorem with a different flavor. So Terence Tau in 2017. So in the case of tau, he takes sigma Rm, and B is a homogeneous quadratic vector field. So each component of the vector field is a homogeneous quadratic polynomial. And also with the condition that V preserves an inner product. So here V times, well, let's put it this way. V at the point x times the vector x is 0. So basically what this says is that the vector field V preserves the, if you take an initial condition, the solution belongs to the same level set. So that shows that this manifold and this type of vector fields are embeddable in a manifold, the Riemann manifold Mg, but here the thing is that the manifold M, so manifold M can be taken to be SO n times Tn plus 1. So the dimension of the manifold depends on the dimension of the space where your homogeneous quadratic vector field lives, and the metric G on M depends on the vector field. You can write this vector field this way, so the HCT is some coefficients EGK GXK. And here, this metric will depend on this coefficient. Finally, the last theorem that we are going to see is 2021. So here, you can take E to be any compact manifold in no boundary. And then there says that the set of vector fields in sigma that are embeddable in the equation is dense, is CK dense for any K, or for any regularity. But the manifold where they are embeddable depends on the vector field. So let me state it more precisely. You take any vector field V or sigma. Okay. You take any K. So positive regularity. And you take any epsilon. So there is some vector field V tilde, which is CK close to V, okay, closer to V in the CK norm than epsilon, and V is in there. V in LG depending on V. So you cannot find a manifold where all of them are embeddable at the same time. It depends on the vector field. Well, you could, I mean, I don't know, but... okay.
So can you give one example of one V that is not embeddable?
That is not embeddable, no.
So in principle, they could be that you can embed any dynamics into the... Oh.
That would be a conjecture, for example, yeah, that any one is embeddable. So the fact that you have to perturb it is it's an artifact of the proof, not of not necessarily true.
But there are like two games going on here, right? Because you know you can fix the G, but then if you let the G vary, then it sounds plausible. You can take any sort of dynamics and maybe if you're clever picking your G.
Yeah, maybe even fix it. I mean, you could even consider this result or something similar for a fixed manifold and a fixed metric. In principle, it's an infinite dimensional thing. But yeah, well, fixed manifold and changing the metric.
So, is there any view of what people think should happen? How many?
No, I have no idea. In principle. So let me show you how the proof goes. It's
V tilde is CK, has a regularity CK?
Yeah. Well, actually, V and W, you can take them to be C infinity, okay, or CK. And the perturbation is CK for K as big as you want. You will see in the proof that you might take V to be of low regularity, C1, C2, CK. But the final V tilde that you embed is same thing. So let me give a bit of time. So I will give a simple proof that has a mistake on it. And then if you spot it, that will be very good. And in trying to fix it, we'll see how it goes. So let me So you take your manifold sigma, you put any metric on the manifold and consider the Laplace eigenfunctions. Laplacian. And now there is an observation. You can try to show this as an exercise. That if you define the map from sigma to Rn, that to any point x in the manifold associates the point u of x given by the first eigenfunction at the point, second eigenfunction, up to the n eigenfunction. This map is an embedding. For n high enough. Okay. So now
PCA, no? It's principal component analysis in statistics. You know, that's what they.
yeah, I think they use this fact in machine learning or this kind of, well, when you have analysis of high dimensional data. So now, okay, we have a manifold sigma, we have a point x, here is our vector at the point x, vx. Let's see what it is here inside. Okay. So, well, I'm not drawing it well. The fact that it's an embedding given by the eigenfunction means that it's going to be very oscillatory, very shaky. It's smooth, but you know, if you cut the image with the En component, okay, the drawing that you get on your manifold are precisely the nodal sets of the n eigenfunction. So it's going to be very. So let's look at, here we have the point Vx, and here our vector field will get mapped to the vector field differential of the embedding at x. Okay. So I'm going to compute who this vector field is. So, okay, consider some basis. The basis is going to be local, okay, but we are not going to be concerned by that. Take some local basis around the point x. And now you can write your vector field V as the components in this basis. Okay. And then this arrow here is going to be given by Vi. Now you are going to differentiate the eigenfunction alpha in the direction of Ei. And now this is the component dy the alpha of this vector field. Okay? So here you are summing over I and summing over alpha. So this gives you a vector field So imagine that these things, these EIs were global. Do not be concerned by that. That's not where the mistake is. So now you say, well, VI, these are just functions on your manifold, right? And EI, and the derivative of the functions in the directions of the EIs are also functions on the manifold. So EI of x is just, you can express this as some coefficients, let's call it beta, times the eigenfunctions. Okay? You expand VI. Now you can also do the same for the derivatives of the eigenfunctions in the directions of the basis vectors. These are functions also. This will be alpha gamma psi gamma. Okay? And now you say, well, I can just truncate these sums to n. I take n big enough. This will be an approximation in CK as good as I want. I just truncate. So if I truncate and plug the result here, what I get is that this vector field is given by, so there is the A, these coefficients, alpha gamma, I beta, and now I have beta of x, beta of x. So I am summing over all repeated indices, and this is the y alpha component. Alpha is here. Okay, call this. So here, this sum over I, you can call it, let's call it this way, V alpha beta gamma. So this vector field is V alpha beta gamma, C beta, C gamma. And now you remember C beta and C gamma for these indices going from 1 to n are precisely the coordinates of your embedding. Okay. So if you substitute now here y beta and y gamma, okay, this is a vector field, it's a homogeneous quadratic vector field defining the whole Rn. And if you restrict it to the image of sigma, is precisely the approximation of this one. So now, if you are able to show that this is a homogeneous quadratic vector field of the type that, where I erase it, so the type that tau was able to embed into the Euler equation, then you have embedded the vector field V and the manifold sigma into the Euler equation. Okay? Because you embed them first into a quadratic ODE and then into the Euler equation. So what's the problem here? So the problem is that so everything is good except so this approximation is good, but this one is not good. If you approximate the derivatives of your embedding, this vector field here is no longer tangent to the image of sigma. Okay. So certainly, yeah, you have created a homogeneous quadratic ODE, but it's not really tangent to your manifold, so the manifold is not invariant in the D. Okay. So what you will need is to, if you imagine that sigma is a manifold that satisfies this equality with a equal sign, so a manifold so that you can find some basis of vector fields. That when you derivate the eigenfunction, this is a finite linear combination of eigenfunctions of the same degree of lower. The same eigenvalue of eigenvalue lower or equal to the one of C alpha. Okay. Then you can do it. So examples of manifolds where this is true is, well, the most simple one is the t-dimensional torus. You have an eigenfunction. If you derive an eigenfunction in the direction of the vector field xy, which is a basis, what you get is an eigenfunction. So the component ky, ki, times cosine kx. So the derivative of an eigenfunction is an eigenfunction of the same eigenvalue. Now you can do this. So if you take vector fields on the torus, and this is also true, for example, in S-dimensional spheres, then you can do this. You take any vector field on the torus of the sphere, you truncate it, and you can embed it into a quadratic ODE. You can show that because of the properties of the eigenfunctions of the torus and the sphere, this quadratic ODE satisfies the condition of tau. It preserves an inner product, and then you can embed it into the Euler equation. Okay, so then this is only true for the torus and the sphere, but now what you do is one more step.
mean, here the torus of the sphere are sigma.
Sigma, yeah, sigma.
Yeah.
In the torus of the sphere on any dimension.
What does it say here? Less than equal to psi, what?
Yeah, so this is a finite linear combination of eigenfunctions of eigenvalue less or equal of the eigenvalue psi alpha. So you are derivating the eigenfunction psi alpha in some direction, and then you want it to be a linear combination of eigenfunctions of the same eigenvalue or of log. Which is, actually for the same eigenvalue, this is the case on the torus on the sphere because of the symmetry. So now what you do is you start with any closed manifold and any vector field, and first, by Whitney embedding theorem, you can embed it, say, in the S-dimensional sphere for D high enough. So now here you can embed your manifold sigma with B. Okay. And now you say, okay, I can smoothly extend B to some vector field set. And now I can embed Z into a quadratic ODE in Rn, and then Rn into Euler, using tau theory. Well, here there is a problem, of course, is that when you smoothly extend Z, okay, and then you truncate it, when you truncate the spherical harmonic or the Fourier expansion of Z, this invariant manifold is going to disappear in general. It's not going to be an invariant manifold anymore. So what you do is to extend V into Z, so that sigma is a normal hyperbolic invariant manifold of the extension. Okay. So normal hyperbolic means local vector is like this. This will be sigma. This is the sphere, so here you have V. And now you can explicitly extend it this way. Okay, so the orbits exponentially approach the invariant manifold faster than any Lyapunov exponent of V. That's what normal hyperbolic approach, or you can also even.
Why do you need this? Why do you need
so that when you truncate Z, you are going to need to truncate Z to embed it as a quadratic ODE. This manifold with a vector field that is close to it survives as an invariant manifold. Because if not, then you are embedding something that has not sigma and V as invariant. And in some cases, so for some classes of vector fields in the sphere and in the torus, finite linear combination of eigenfunctions, then you can embed them extra. So for example, you can embed any annus of flow, since they are stable by perturbation. You can find it as an invariant subset, finite dimensional, of the Euler equation and some Riemann manifold. You can also embed, for example, a chaotic vector field. So the lowest dimension, you are able to find chaotic vector fields that are just finite combination of sines and cosines in the three torus, for example. And then what you get is a chaotic invariant set of the equation in a manifold of dimension 22, the lowest one. Okay. So the dimension of the manifold can grow very fast. Just so to finish with an example of how fast it can go. So this result was used by so there was this question about the Euler equations being something that is called Turing complete. It basically says you can encode any Turing machine in the flow lines of the dynamical system. So Cardona, Miranda, and Peralta Salas they showed using this result that the Euler equation is Turing complete, but the manifold what you get, the dimension is something like 10 to the 31. Okay? So this is infinite. Really. Yeah, so the dimension can grow pretty fast with because at the end of the day, the dimension depends on the number of spherical harmonics or Fourier coefficients that you take to approximate your vector field. You can actually compute an explicit bound using Jackson's theorem, for example, about the approximation of functions by polynomials, but it grows very fast. So I'll stop there, and thank you very much for your attention.
Are there any questions?
So when you embed your vector field in this Euler equation, and that you know at the beginning that your vector field has some property, for instance, you have a Km tori or structurally stable in the case of another flow, how does it translate in the Euler equation?
You mean as a property of the actual full Euler equation? You don't know.
At least locally you have some
if you perturb a little bit, so you have this, imagine, say, a 3 manifold inside your space of the various free fields. You don't know what happens if you go a bit outside this thing. Yeah? I mean, maybe you can do something about it. If you actually, you can compute very explicitly how these vector fields look like in SON. So they live really in a very SON times Tn, right? So this is not some very abstract Riemannian manifold, it's very explicit. So you can understand very explicitly what they look like, and maybe you could do something. But in principle, if you exit a little bit from this very, very small invariant set, maybe there are not even global solutions generically. And this is related to a problem I'm going to speak about in the open problem session that I think is going to be interesting to the finite dimension.
Any more questions? At which point did you use these are like eigenfunctions? I mean, like in your computations?
No, well, I use it really in the case of the torus and the sphere to show that this OD satisfies the Gauss condition. But in the mock proof I gave, you don't need to use eigenfunctions really. You could use any L2 dense sequence of functions. And if you find, for example, this is so find some L2 dense sequence of functions. Yeah? So that satisfies this from some class of vector fields in your manifold, and then you can do the same thing directly. Yeah? But I think that's an interesting problem in itself, actually, to study manifolds or functions that satisfy this property. Where the derivative becomes a finite dimension, let's say, breaks into operators in lower dimensional spaces or your space of functions.
We not are EI of X, they are just a local frame. It can be.
Yeah, here they are like a frame.
They're not parallel transported.
No. In the case of the torus and sphere, they are. You will take the ones that generate the isometries, and that's why, in that case, when you derivate an eigenfunction by a vector field that generates an isometry, it's a linear combination of other eigenfunctions. Gives you a representation of the isometry.
But general manifold.
General manifold, yeah. Well, you could, on a general manifold, you could even consider these do not have to be a basis really. In general, you will not have a global basis, but you can take some bigger collection, globally defined, that at each point a subset of them defines a basis. And then you could do the same thing. This for the proof, this is not necessarily. You just need to be able to express any vector field as a linear combination.
No more questions? Another one.
I have a question. So, if you can embed, for example, an anosov flow into your Euler fields, yeah, and you can also embed the invariant measures of these anosov flows into this. Have they any meaning meaning, or are they of any interest for understanding the fluid dynamics, these invariant
In
measures?
general, building global solutions of fluid equations with some interesting dynamics, it's an interesting problem in itself. But in the global, let's say from the point of view of a physicist, imagine, that is interested in the actual qualitative dynamics of this infinite dimensional thing, I don't know what.
Okay. So let's thank Paco again.